Lesson 1A.11, End behavior of a polynomial. Consider the function f of x equals 2x squared minus 4x plus 1. If I ask you to evaluate f of 3, option 1 is just plug it in. I can take 2 times 3 squared minus 4 times 3 plus 1. 3 squared is 9, 9 times 2 is 18, minus 12 plus 1, 18 minus 12, that's 6. 6 plus 1 is 7. F of 3 is 7. Option 2 is I could graph the function, look at the calculator, and say, okay, f of 3. Notice that this is 2, so this is 1, 1, 2, 3. So 3 is right here. And then go up to find the graph on the y-axis, so that would be, hey, look at that, 7. F of 3 is 7. The value of the function at x equals 3 is 7. The height of the function at x equals 3 is 7. So there we go. 7 is the height of the function at x equals 3. That's all well and good, but I've got a new question for you. This notation you probably have not seen before. So this would be the first time this year in pre-calculus that you've seen something that you've never seen before. This is called a limit. The limit is the foundation of calculus. We did not have a subject known as calculus until the concept of the limit was finally established. A limit is the intended height of a function at a given value. This statement is read, the limit as x approaches 3 of f of x. LIM is an abbreviation for limit. So we say the limit as x approaches 3 of the function, which is f of x. Again, it's the intended height of a function. The way I determine what a function intends to be is I find x equals 3. Okay, here's x equals 3. And I don't look at x equals 3. What I'm actually going to do is I'm going to look near x equals 3. Imagine that the function itself at x equals 3 is covered up, and you use the evidence around the function to help you figure out what you think the height should be. Well, if I follow the graph from the left, if I follow the graph from the right, it looks like we're headed to some location in this general vicinity. Now, the closer I get to the actual value, let's try to get a narrower rectangle. So the closer I get to the actual value, the more accurate my answer is going to be. So if I'm looking for a limit, I can think about, well, don't evaluate it at 3, evaluate it at 2.9, or better yet, 2.99, or better yet, 2.999. All of those values are getting closer and closer to 3. If the left side and the right side of the graph are headed to the same location, then we say that the limit exists at that location. So in this question, the function value at 3 is 7. Well, the intended height is also 7. Now, in this particular example, the fact that the limit is equal to 7 and the function equals 7 is not particularly useful. It's the same value no matter what. What's the intended height? What's the actual height? It's 7 no matter what. What a silly thing to ask. But if I give you a graph that looks like this, where there's a hole in the graph at, let's say this is 3, and I say, okay, what's f of 3? Well, f of 3, there's a hole in the graph. It's undefined. But if I say, what's the limit as x approaches 3 of f of x, I'm not asking what the actual value of the function is. The actual value is undefined. The intended value is wherever that hole happens to be. So let's say it's at 4. Well, the intended value is, in fact, 4. A limit allows us to see where a function is going, even if it never actually makes it there. An undefined function value is no problem when I'm asking you for a limit. It's just a different way of asking the question. Instead of asking where is the function, the question is asking where is the function going? Evaluating a function, where are we? A limit, where are we going? Now, a major concept of this course that we're going to develop over the year and then really hit hard at the beginning of next year in calculus is the idea of continuity. A function is called continuous at x equals a if the limit of the function and the value of the function are the same. Notice the limit and the value are the same, so this function right here is continuous at x equals 3. Now, it's a polynomial. Polynomials are continuous everywhere. I knew that it was going to be continuous at x equals 3 because this is a polynomial. But now I can give a formal argument as to how I know it's continuous. It's continuous because the limit equals the function at all possible values. No matter which point I pick, I can pick any point, the intended height and the actual height will be the same thing. Notice here, same graph, plug in -1. Well, at -1, which is right here, the function height is, hey, look at that, it's 7 again. So f of -1 is 7. The limit as x approaches -1, since the graph has no holes, breaks, skips, or jumps, this graph is continuous at x equals -1. So that means the intended value will also be 7. No tricks, it's just a different way of asking the question. Which leads us to this question. F of x is still the same graph, but now it doesn't say the limit as x approaches a number, it says infinity. If I ask you to evaluate a function at infinity, that question makes no sense. Algebraically, it is not legal to evaluate a function at an undefined value. Infinity is not a number. Infinity is a direction. Infinity is a destination. I can never actually reach infinity, so it would not be legal to actually evaluate the function at infinity. But with limits, we're not evaluating at infinity. We're asking the question, where is this function going as x approaches infinity? So if I look at that graph again, as x approaches infinity, okay, this direction is x approaching infinity, x approaches infinity. The function is the graph right here. So as the graph goes to the right forever, I want to know where is f of x going? Well, since as we go to the right forever, the graph is going up, f of x is going up, f of x is also going to infinity. So I would say that the limit as x approaches infinity of f of x is infinity. Anytime I ask this question right here, the limit as x approaches infinity, what I'm asking is the right end behavior. Is the graph going up forever? Infinity. Is the graph going down forever? Negative infinity. Or is the graph leveling off to a particular number, like if we had a horizontal asymptote, and the graph is leveling off to, I don't know, 7, right? So limit as x approaches infinity, I want you to look at the graph and tell me, as the graph goes to the right forever, what is the height of the function intending to be? In this case, the graph goes up, so the graph is going to infinity. Notice I could extend this question into limit as x approaches negative infinity. If we're going to negative infinity, that would be the left end behavior. As the graph goes to the left forever, x approaches negative infinity, where is the curve going? Well, the curve is going up again, so it would be the same answer, infinity. Both the right end behavior and the left end behavior for this graph are going up and up. Let's change one thing in the function. Notice it's now negative in front. It was positive in front. Now it's negative in front. Still asking the same question. But I don't need to waste time graphing this because I'm a pre-calculus student and I already know what this graph looks like. It's quadratic, which means it's a parabola. But the leading coefficient is negative, which means it's a parabola opening down. The other terms don't have any effect on whether the graph opens up or down. a quadratic opening down. Right end behavior, what's happening on the right side of the graph? It's going down, and it's going down forever, so that would be negative infinity. Left end behavior, what's happening on the left end of the graph? It's going down, so negative infinity. Limit to positive infinity, limit to negative infinity is just asking in what direction is the graph going as we go left and right forever. End behavior. So let's summarize using something called the leading coefficient test and its effect on end behavior. Consider that we have a polynomial. Remember, this rule only applies to polynomials. As we get into rational functions, we'll learn how to adjust this rule. As we get into logarithms and exponentials, we'll learn completely different techniques. For a polynomial, remember that a polynomial is just a sum of a bunch of individual terms. A sub n, x to the n. X to the n just represents the leading variable with the leading degree. A sub n represents the leading coefficient. The leading coefficient is a sub n. So this is an nth degree polynomial. And then there's a bunch of other terms. But as we saw, it's really only the leading term that tells me what I need to know. The negative 4x and the positive 1 don't tell me what the end behavior is actually doing. So when n is even, so if we have an even degree, remember second degree, fourth degree, 16th degree, an even degree, and the leading coefficient is positive. So even degree and the leading coefficient is positive. We always start with the right end behavior, always start with the right side of the graph. If it's an even degree and the leading coefficient is positive, the right end behavior will be positive infinity. If it's an even degree and the leading coefficient is positive, the right end will be positive. So the right side goes up. Now, making some connections, an even degree is not the same thing as an even function. An even function has to do with symmetry. The right side and the left side are the same. But they are related. An even degree means the right and left side end behavior will be the same. The left side will go up as well. The graph could do anything in the middle, but if it's an even degree, the right and left side will be going in the same direction. We don't necessarily have symmetry because I'm not describing this as an even function. I'm describing the degree as an even number. So if it's an even degree, the left and right side will agree. Fourth degree, 10th degree, 28th degree, the left and right side will agree. So if the right side is infinity, the left side is infinity. Notice if the leading coefficient is negative, then the right side will be negative, and then the left side will agree. So we'll have right side down because the the coefficient is negative, and then left side down because the degree is even. No idea what's happening in the middle, but the right side and the left side will agree. Even degree, left and right agree. If it's an odd degree like x cubed, right side goes up, left side goes down, left and right side disagree. Odd degree, left and right disagree. If one side goes up, the other side goes down. If one side goes down, the other side goes up. So if it's an odd degree, the left and right side are going to disagree. A positive leading coefficient means the right side is positive. A negative leading coefficient means the right side is negative. We always start with the right side. So positive right side is positive, negative right side is negative. Positive right side is positive, negative right side is negative. Even degree, left side agrees. Even degree, left side agrees. Odd degree, left side disagrees. So right side up, left side down. No idea what's happening in the middle, but right side up, left side down. Odd degree, left side disagrees. So if it's a negative coefficient, the right side goes down and the left side disagrees on an odd function. So we can use the leading coefficient of a polynomial to quickly and easily answer limits to infinity and limits to negative infinity. So for each one of these, let's consider the end behavior. Now, notation is important. On the AP exam, you will be asked this question to determine the end behavior of a function. It's on the free response question 1. And if you don't use proper limit notation, you will not earn the point. Determine the end behavior. If it's the end behavior, I'm going to say limit. Directly below it, I'm going to write x approaches infinity, and then I'm going to name the function f of x. So the limit as x approaches infinity of f of x is, well, this is a quadratic, but I really only care about the leading term. It's an even degree, which means the left and right side are going to be the same. And then the leading coefficient is positive. So if the leading coefficient is positive, the right side is up. And then the left side, limit as x approaches negative infinity of f of x. Because it's an even degree, we're going to agree. So positive leading coefficient tells me the right side is up. Even degree tells me the left side agrees with the right side. So pause here, try the other ones, play when you're ready. So limit as x approaches infinity of g of x, make sure you're naming the function properly. So this one, the leading coefficient is positive, so infinity. Limit as x approaches negative infinity of g of x. Since the degree was odd, the right side and the left side are going to disagree. Question C, the limit as x approaches infinity of h of x. The leading coefficient is negative, so right side is down. And then the limit as x approaches negative infinity for the left side. Since it was an even degree, the left side and the right side are going to agree. And the last one here, the limit as x approaches infinity of k of x. Now, be careful, this one is not the leading term. This one is the leading term. The leading coefficient is negative, so the right side is down, negative infinity. And then the limit as x approaches negative infinity for the left side of k of x. It's an odd degree, so we have to disagree, negative infinity on one side, positive infinity on the other. Same question, but this time the polynomials are in their factored form. It really doesn't make a difference. The process is still the same. I'm still doing the limit as x approaches infinity and the limit as x approaches negative infinity. I need to know the leading coefficient and I need to know the degree. Now, the degree is pretty straightforward. Linear, linear, linear. First degree, first degree, first degree. If I multiply first degree times first degree times first degree, this is going to be third degree. So I know my two answers have to be opposites. Leading coefficient, just imagine if I were to multiply these together, the leading term would just be x times x times x, or x cubed. The leading term is 1x cubed. Leading coefficient is 1, so right side up, left side down. Go ahead and pause here, try the other two, hit play when you're ready. Limit as x approaches infinity of h of x. Limit as x approaches negative infinity of h of x. So I see if I were to multiply these together, keep in mind the leading term would just be negative 2x times x squared times 2x. If I multiply those three terms together, the leading term actually ends up being negative 4x to the fourth. Leading coefficient is negative, right side down. Degree is even, left side agrees. And then lastly, the limit as x approaches infinity of g of x. The limit as x approaches infinity of negative infinity of g of x. So leading term, if I took this guy, this guy, this guy, and this guy, so the leading term in each factor gets multiplied together. Keep in mind, if I add 4 to the end, that's going to have 0 effect on my leading term. So I'm just going to multiply those 4 terms together. So a negative, so it's going to be a positive 1 x to the 4, 5, 6. So my leading term is positive 1 x to the 6th. Right side is positive, so up. It's even, so the left side agrees.